Okay, let's start just in case we need more time later. So, welcome tutorial Decoded Quantum Interferometry. I leave this here for us to keep the big picture. I might use this part for the notation of preliminaries, and then I leave it on. The tutorial is very from scratch and very slow paced. So everything I say should be clear at all times. If anything isn't clear, please ask just in case. And yeah, and if I feel like we're during a conversation, we can keep later. We can go later. Okay, so let me first tell you about both combinatorial optimization and error correction very briefly, and then we'll get to the meat of what this quantum algorithm is and what it does. So let me introduce a decision problem called source set, which is defined on n bits and constraints and larger than n, and over a domain of length n bit strings. In particular, it's specified by a matrix B and a vector V, such that there's a system of linear equations that looks like a normal system of linear equations. And everything, yes, everything is modulo 2. And, okay, sorry. And instead of writing this all the time, I just write this mod 2. Now, the exact source set is a decision problem, and the question is, given B and V, does there exist an X such that P of X equals V? And okay, let's make this interactive. Raise your hand if you think this problem, as specified, is in P. Raise your hand if you think this problem, as specified, is in NP. This is an easy problem because you can do Gaussian elimination and just check. Gaussian elimination. Meaning not so interesting for us today. From this, we can define a decision problem called max source set. And satisfaction, satisfactory source is the addition modulo 2 of several variables. And for this, we introduce a function, which is just, I can define it formally once. And I will not use this notation a lot, but for now it's a bit better. This is the ith row of B. So I define this as a cardinality of a set. This is just the number of satisfied constraints. Now, from this, the decision problem becomes, given alpha smaller or equal than 1, question, does there exist an X such that S of X is larger or equal than this. So this is a fraction of m. So is the maximum fraction of satisfiable constraints more than a fraction alpha of the total? Now raise your hand if you think this problem is in P. Raise your hand if you think this problem is in NP. What did you say? Okay. So this problem is in NP and is NP hard, if I remember correctly. Okay, it's NP hard. And it's related to sharp P maybe because you can count things. But as stated, it's an NP hard problem. And this is the problem we'll be talking about. And I phrase it as a decision problem. In practice, we have like the realized version of Max Sorsat, which is find something like this. So we're just looking for the bit string that satisfies the maximum number of constraints. This is like we don't expect polynomial time algorithms to do this in general, neither classical nor quantum. But with this figure of merit, we can benchmark algorithms against each other. Algorithm 1 versus algorithm 2, we just run both of them, see what they output, and then we check what the score is of one relative to the other one. And with this, we can say algorithm 1 is better than algorithm 2. And further, if there was like one standard benchmark class, we could fix alpha, like an alpha star ahead of time, and say good algorithms are those which achieve a fraction larger than this alpha star. Algorithm 1 is better than algorithm 2 if and only if a fraction of satisfied constraints of the first one is better than the second one. The fact that this is NP hard also tells us that we don't expect one algorithm to be better than all other algorithms in all possible instances. Rather, any algorithm that does well will exploit some amount of structure, and then like no free lunch. The fact that you do well in some instances will necessarily mean you do less well in some other instances. And in my language, this tells me that trying to give algorithms for max Sorsat is a game of parameter regimes. There will be some instances where one algorithm is a bit better, and some other instances where it's less better. Now, if we had less time, I would now keep going, but it will make sense at the end to introduce this other problem, Linsat, or Max Linsat, which is a generalization of Max Sorsat. If you want to drop out now, is a good time, and I'll tell you when you wake up again. In Max Linsat, we have n p symbols and m constraints, and so we still have m larger than n, and now we also have r sized satisfaction sets, satisfiability sets. Now, instead of having bit strings, we have these p symbols, which I write this way, and fp is the cyclic group of order p. So let's make things easy, and let's say that p is prime, so that weird stuff doesn't happen to us. So it's like a cyclic ring. So addition and multiplication are well-defined modulo p. Now we have, again, a matrix B. And now, instead of having a vector, we have a set of sets, all of which are subsets of the ring, and all of which are of a fixed size, which we need to agree ahead of time. Then, again, now we have something like a system of linear equations. But now we, like on the right-hand side, instead of having equality, we have set containment. So we read this as Bx in F. And everything is again modulo P. So I can ask you if you think P and NP and stuff, we clearly see that this is a generalization of that, where for that we chose P equals 2, there are two symbols, 0 and 1, and R equals 1. Each set is one-dimensional, like has only one element, which can be either 0 or 1. So from max source set, we made larger the domain where the variables are involved, and also we made it a bit easier to satisfy a constraint. Because imagine if P was 500 and we only had equality here, then the chances of things converging in a way so that you get the right choice out of 500 choices would be very small. And this way we will be able to tune this as a hyperparameter. Yes, S in this case is defined analogously. So we have M constraints. We can ask for given S, for given X, how many of those are fulfilled. Just like the indicator function we would use now is a set inclusion instead of equality. But S is defined the same way, and from S we can define the real life max Lin set. I don't know, I would guess not, because Gaussian elimination should also work. Well, this has I think if R is larger than 1, you can rewrite it as a larger instance of the same problem where R is 1. You just have more constraint. You turn every constraint with the set into R many constraints with equality, and you don't care which one of them is satisfied, as long as one is satisfied, you're good. And then you do Gaussian elimination, making sure that you satisfy one constraint from each of this set of constraints. That's what I was trying to say. It should work. No, but like sorry, like source Lin set should, what I was trying to say is that Lin set should be as hard as source set without the max. But I don't know. We can check afterwards and we keep going. Yeah. So, okay. You do this because then you can benchmark against random guessing. We expect that random guessing should be the worst algorithm. And here random guessing satisfies about half the constraints. And here we'll pick R to be about P halves, so that random guessing will also satisfy about half the constraints, because then it fits in the standard language of bad performance is 1 half. Linear. So now this is an arbitrary linear combination. That's also an arbitrary linear combination, but in a way that because you define it in bits, it like the algebra is replaced by XOR. No. NP hardness, as I introduced it, No, sorry. I'm lying. Yeah, here I get a bit lost, and I think Max will be better at answering this. So I think it's NP hard, worst case over alpha. So there exist alphas for which this is NP hard. For some typical problems, 7, 8. For Max, it's 7. Okay, good. Yeah, but okay. So this is Max lin set. That's Max source set. It's good to introduce this. It's good to think in terms of that for most of the time. So this is a bit easier to think. Okay. And now, very briefly, the decoding problem, what I would call the decoding problem. I introduced it once abstractly because I used to complain that people don't do this, and then I show you in practice. So let's say you at home have a bunch of messages you want to send through channels and stuff, and then there's a code, which is a set of code words. Code words are a subset of all words. And for each of these things, there's like a fixed length that we agree ahead of time. And these code words are longer than the messages you're trying to send. Then the process of encoding is going from a message to a code word. Decoding is going from a code word to a message. The inverse of encoding, clearly. Then we have errors, which map from the set of code words to the set of all words. And this is a problem because decoding not defined for all words. And here's where error correction comes in. Where you map an error applied on a code word back to the code word, or maybe also the error. And introduce this because this is the way language makes sense to me, but I will abuse language and say that the decoding problem is error correction. So I'll say things like what errors we can decode, how many errors we can decode, and things like this, which is not exactly what one would expect under decoding, but it's what I'm used to by now. And then we'll be talking specifically about linear codes. Which are defined on n bits n checks m larger than n, and careful, I called n the word for bits before. This is confusing, and there's no way out of it. It's just confusing. We need to remember if we're talking about optimization or error correction. And there's an n times n parity check matrix H, which defines a linear code or a class of linear codes, where the set of code words will be the kernel or the null space of this matrix. Notice code words have length n. Now, if I give you given H, it's easy to find G, generator matrix, such that G of X equals C, so that you can go quickly from messages to code words. No, the message is a bit shorter, and given C, you figure it out. It's also easy to figure out. No, we will not use messages at all, just to be complete. And so H is m times n, and G, so it's the sizes, the dimensions of G are n times n minus k, and the code length is n minus k. It's something you compute. And what it is depends on how good the code is and things like this. Yeah. G is a generator matrix. And it's something I introduced once. It's the thing you would use if you wanted to go to generate code words for given messages. And given G, it's usually trivial to extract X from C, because in some canonic form thing, G will be the identity and then something else, meaning the first few bits of the code word will be X. And that's cool. No, because it's not square. But it's something that I converted, yes. Yeah, so this part tells you that it's very easy to go from X to G and back. Now, one reason, I didn't tell you, not very important. Like G is some sort of indexation of the bit streams that generate this part. Not very important, but just so that you know that these things exist and that it's easy to find them. Okay, and then one reason linear codes are cool is because of how they relate to errors. Let's say we took a code word and we applied some error. Now we have a word that's not a code word anymore. If we act with the parity check matrix, we will find something that we'll call the syndrome, which, so I'm just taking this and I'm multiplying it from the left by the parity check matrix. By linearity, this will become a sum of the parity check matrix on the code word plus the error. But by definition, this is like the first part vanishes, because that's how we define the linear code. And this thing I will call S, and it has size n. So N is the number of checks, M is the number of bits. We take M bit string errors, we act on them with the parity check matrix, we're left with N bit string syndromes. And in this case, the decoding problem is given S, find E. Now, H doesn't have the right sizes to be invertible, so H is not invertible. So going from E to S is very easy. Going from S to E is less easy. Raise your hand if you think this problem is in P. So given all the definitions we've given an arbitrary S, return the corresponding E. Correct. Yeah, I don't have the decision problem formulation. I mean, like, you could formulate the decision problem for all the bits and stuff. Do you think this is solvable in classical runtime? Raise your hand. Do you think this is verifiable in classical polynomial runtime? Raise your hand. Cool. Yeah, this is something like NP hard in general. And yeah, if I'm saying things that are not formally sensible, that's possibly true, and I will insist we ignore it. But
no, it's just like the multiple errors that are
yeah. Yeah, whatever.
Okay, so yeah.
It's still hard. I mean, finding one out of three cannot be harder than finding one out of one. Yeah. If you want to control how hard this problem is, things you can change are the Hamming weight of the error, things like some structure of the parity check matrix, in particular its sparsity, and in particular not properties of S. So in principle, if I just show you a syndrome, you will not be able to say anything about how easy or hard it will be to decode that syndrome. And now we say, like, given H, yeah, the hardness of the decoding problem does not depend on properties of the game. Okay, this statement is, if I say it this way, is not so interesting. But like, if we want to analyze the hardness of the coding, we will not check for specific, we will not demand that S fulfills specific properties. I mean that S, like the coding problem can be easy or hard, independently of whether you demand S to be sparse or non-sparse or fulfill specific. Okay, we can forget about this. Just like if you try to familiarize yourself in which cases things are easy and which cases things are hard, the things you would find written in the assumptions of the theorems would not be properties of the syndromes. Sure, I guess. I'm not sure because they have different sizes. But 1 second. No. Now, the decoding problem is hard in general, but in principle, nobody forbids you from just proposing a decoding algorithm, which given a syndrome will output something, and you'll be able to verify whether it works or not. So given a parity check matrix, we can think of a decoder, and then we say, we can decode L errors up to L errors if the decoder is correct Hamming weight is up to L. This is a bit confusing because we're not talking about how many different errors there are, as in like different error vectors that would cause this, but still this is the language we use. And just to spell one thing once, that if you do counting argument, because there are many more errors than syndromes, like for arbitrary errors, we expect many collisions, meaning S, which is the syndrome for E, equals S prime, which is the syndrome for E prime, with E not equal E prime. And this is a problem, because this tells you that if the input to the decoder are the syndromes, and two different errors give the same syndrome, no chance you'll be able to say what error caused this syndrome. And a different way of saying this, no collision is a necessary property for decoding, or correct decoding. And this kind of tells you why the Hamming weight of E can have a say in this. Because one way to prevent collisions from happening is just reducing the legal space for the errors. In principle, if you're doing things wrong, it could be that you have very low weight errors that still cause collisions. If that happens, then you are sad, and that is not a very good error correcting code. Cool. Now, with this, the next part will be very quick. I leave this here because it has all the definitions that we care about. Okay. Now, we have, on the one hand, Max source hat, where we have this B matrix and the vector of right-hand sides, which specified a system of equations of this form. And now I'm calling Y really the thing that would be the output. So V is what you want Y to be. Now I'm calling Y the actual output of this multiplication. And on the other hand, we have the dual linear code, which we call C perp, which is the error correcting code you get if you take B transpose as the parity check matrix. So now I'm defining an error correcting code that's based on the max suicide problem we're trying to solve. And here, the system of equations you get has the opposite shape. So we have a fat matrix, long errors, short syndromes. And here we have correct the coding for a given syndrome. If for a given S, we find the correct E. And here our figure of merit was the number of satisfied constraints, which now I write as this. So, yeah. Yeah. No. Okay. Yes. If E can be any possible error, then there will be collisions. Collisions kill you. So the path forward is not allowing E to be anything. You will restrict what errors can be. I think the notation C-perp is inherited from classical linear coding theory, where for any code you can define its dual. And the dual of a code is where you just transpose the parity check matrix. So if you're, yes. And this is, I don't know about this, but I have a feeling dual codes make sense when the shape of the matrix is something specific. Otherwise, you're left with a nerve correcting code where you have more checks than variables, and that's weird. Okay. So the distance between V and Y. Now I defined Y like for every X, this is the actual output, and that's the output we want. And so this says if V equals Y, then we satisfy all constraints. If the distance between V and Y is M, then you satisfy no constraint, and you have all the between steps. And I wanted to write it this way because then this feels like a closest vector problem. And on this side, feels like a shortest vector problem, assuming that we said that the Hamming weight of the errors would be limited. And if we look at it from a distance, we see that these are just two different linear systems of equations that we're trying to satisfy. The relation is that we just took the matrix of coefficients and transposed it, and this kind of changed the problem. And this is what this duality is. We take a problem where like the rectangular matrix is well defined, and we just transpose it, and that defines a different problem. This is called Vegas reduction. And don't quote me on this, but as far as I know, this was the new technique used in proving that learning with errors is difficult. So okay. And in what way? There is one way in which this is a quantum reduction, and we'll get to that later. But this is cool because we're reducing one NP hard problem to another NP hard problem, so we're not breaking anything, but it's cool. They are, okay, we'll get to that later, but they're related by a Fourier transform. So sampling, like having the ability to no. Okay. We'll get to that later. And yes, I didn't make good management of the boards. Yeah. It's like duality in the abstract sense that two things are related somehow. Yeah. Yes. So the duality shows up in that doing good in one side allows you to do good in the other side. And this. Okay. I will delete this to be a bit more efficient. Sorry. Mm-hmm. Yeah, I'm sorry I'm being a bit slower than I had anticipated. I hope that's okay. Okay. Now, I'll briefly introduce a primitive of sampling algorithms for combinatorial optimization. Meaning, in Max Linset or Max Sourceset, we had, like, our goal was to find something like the bit string or string of symbols that satisfies the most constraints. And one possible strategy, come up with a distribution P such that you sample X according to P and P of X biased toward large S. Now, this is something you could do, and two reasons why you might consider this. One is because we already said that we don't expect being able to solve the problem in all generality. So this gives us a way to maybe try our best to getting close to it without failing spectacularly. And sampling bit strings from a specific distribution sounds like something we can do with a quantum computer. Now, in this strategy, the performance metric, like the thing we will compare algorithms against, is the expected number of satisfied constraints. So for any probability, we sample x's and we just ask how good are we on average. And for example, we could prepare a quantum state, psi, which is of this form. Like this is like the easy example of what this would look like. Then the probability of measuring x, if you perform the computation basis measurement of this quantum state, would be higher for bit strings that have a higher S. Now, this is cool, but with this one, maybe the distance between the good bit strings and the very good bit strings doesn't get very well separated. And in the end, even though we're sampling many good bit strings, for the expectation, the less good ones still show up. And so the cooler version of this would be to prepare a quantum state that now we call the DQI state, which is a strict generalization of this. So instead of taking simply the objective value, we say, let's take some function of this objective value, and in particular, let's take a polynomial of that objective value with a fixed degree. And that should make it easier for us to be able to bias more towards the good fit strings, in that we separate better between the good ones and the very good ones. Now, in this approach, you can believe me that choosing the parameters that maximize the expected value is easy, but it takes a long time to derive, so I will not do it, just you can believe me. And then the only thing that's left is the expressivity, quote unquote. So I'm telling you, if we commit to using these polynomial distributions, then I'm also telling you that once we fix the maximum degree, then I have a way of picking the optimal coefficient. So then the only design choice we have is what the degree of this polynomial, and that's kind of the resource that we'll want it to be high, but it will be expensive for us to make it high, and we'll try to make it as high as possible. Okay. Does this make sense? I'm presenting this as something you could do, not necessarily as this is obviously the best way. Yes. Yeah. 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 Yeah, I mean, that's one way of saying it, but don't think of it in terms of amplifying. Think of it in terms of, if I give you this superpower, like the superpower of preparing this quantum state, then the higher the L, the better. I don't give you the superpower of taking arbitrary functions. I give you the superpower of taking polynomials up to a fixed degree, because this will be the resource. Because, okay, do we agree that the expected performance using the optimal distribution of this form will be higher than this? Just because this is a special case of this. And no, also, like, the difference between, so let's say you have two different x's, one achieves 10 and the other one achieves 100, and you want to boost the probability of obtaining the one that achieves 100. If you have a probability distribution where the first one, like where the ratio is 10 to 100, you will see the bad one much more often if the ratio was 10 to the 50 versus 100 to the 50. Like, it eventually becomes very close to infinity if things go well in specific cases. Now, did all of this preliminaries, because now I can tell you exactly what is in this paper, and from this you can decide if you want to read it. Yeah. Yeah. Yeah, it depends on everything. Sorry. Let me rephrase. Can depend on everything. It turns out that the optimal choice of alpha only depends on B and not on V. It can be anything, but it's real positive numbers in this case. Potential. Okay. Later, I wrote it in alpha because it would make sense. Eventually, you move into different bases where it makes less sense, but it is easier to analyze. The coefficients in that basis are definitely positive real. Here, I can't guarantee. Okay. So the result is they give a quantum algorithm to prepare this state, the one that we described. Then they spell out the reduction as a duality, because if you're very awake, you'll notice that I put here L and not a different letter, because here the expected performance on max Linsat, which we said is a function of the degree of the polynomial, is on one-to-one relation with the performance on the coding problem of dual code, measured in number of errors we can decode. And the trick is a Fourier transform that I hopefully can spell out in simple terms. And then one of the main results is the predicted expected performance for which they don't need to run any quantum algorithms or any simulations. They prove that asymptotically the fraction of satisfied constraints scales like this. I mean, not scales like this, is this. Remember, L is the number of decodable errors, M is the number of constraints, P is the order of the cyclic group, R is the size of the satisfiability sets that we can boost, and the other ones are the same. And because there's something called the semicircle law, if we talk about the special case max XOR, we recover slightly simpler formula, which if you plot L divided by M, S divided by M, looks like this. 1. 1, but it's physically impossible to get above a certain value. It's like, this is what the formula, this is what the thing looks like, but you don't expect to ever get very, very high. But this is the semicircle law. And that the number of decodable errors gets close to the total errors, to the total number of errors. So M is the length of the errors, which is the same as the number of constraints in max XOR. What's physically impossible is to get a decoder that can okay, I was coming from the other side. So I'm saying that it's physically impossible that the number of errors you can decode is close to all errors. L over M, by definition, is maximum 1. In practice, it will not get close to 1/2. It will be smaller. Or it could get, I don't know, 1/2, 1/4, something. Okay, I don't know if now is a good time or not, but I made a handout. You can keep one, share with your neighbors, because there are not so many, and pass the other ones, of like a bare bones mini example of how this looks like. So I show a tiny problem where I write out all the all the intermediate steps and what things look like. You can pay a bit of attention to it right now. When it gets to the quantum algorithm, stop reading. And the idea is that when I present the quantum algorithm abstractly, you're able to follow it step by step for the specific case. And yeah, it's printed on both sides. Okay. Cool. Okay, Okay, now I'll write down the quantum algorithm. Before I draw it, before I draw the circuit, I will need a leap of faith. First, let me rewrite the quantum state that we want to prepare. And now, believe me, the Fourier transform of this quantum state has a very nice form. And notice that when I say the Fourier transform, I mean the bit string Fourier transform, not the scary QFT from Nielsen Chong. Like here, the Fourier transform is like the two-dimensional, like the n-fold product of the two-dimensional discrete Fourier transform, which is just the Hadamard gate. Now, first I write it down and then we go step by step. And I write it down for Max Sorsat. The general case for Max Linsat is a bit more messy. Okay, so I wrote down this monster. Let's go step by step. Notice that on DQI, we were summing over all possible solutions to a problem, all possible bit strings. Now we sum over all possible syndromes. For every syndrome, we again have a similar sum as we had before. So the degrees of the polynomial kind of decouple in different branches. Now we changed the letter we use for the coefficients. Now we're using U. And what I said earlier, that picking optimal alphas kind of a lie. What's true is that it's easy to pick optimal U's, but for all we care, that's okay. There's a normalization that counts how many errors of a given weight there are. And then inside, for every syndrome, we sum over all errors of a fixed Hamming weight. So this is where the different branches decouple. There's a phase that relates to whether an error corresponds to the right-hand side of So if you look here, if we check the shapes of things, we see that X kind of corresponds to S and Y kind of corresponds to E. So we see these now that we sum over all M bit strings, which I call E because they make sense here, but we check if they agree with the right-hand side, meaning they play the role of Y. And then of all of them, we keep only the error that corresponds to the syndrome we're summing over. So this is a very big sum. Only one term will survive. That term will be weighted by the weight of the error, and that will be the amplitude. UK is neo parameters. They play the role of alpha, but now we went to a different basis. So these are positive, real positive, and these ones are nice and they're already normalized. So, oh no, okay. Let's keep it this way. Yeah, sorry. This was a bad choice of me. This S and this S are not related. Yeah, this is the leap of faith. So said otherwise, the Fourier spectrum of this function looks like this. No, it's here.
But then it's a specific X. It's not just any
function. Sorry, I made a mistake of using S, but like Max Sorsat is specified by B and V.
you max it from that. And then we use the S that's below it.
Yes.
And for that one.
Which, okay, I didn't write it, but every problem, no. S of X is always the number of satisfied constraints. Cool? The Kronecker delta. So this is 1 when these arguments are the same, 0 otherwise. So this, okay, I'm not very good at visualizing Regex reduction, but you can start to see where this duality Fourier stuff comes. We have this function, and what we're saying is that the Fourier spectrum of this function is super sparse and known as long as we know what errors correspond to what syndromes. Even further, in case you can make the jump, we see that the condition of no collisions shows up here, because if there were several errors causing the same syndrome, then the phases would add up and then cancel or not cancel, but like they would break normalization and all sorts of nasty things. So analyzing this requires the no collision, but we get the no collision for construction from what we said about the decoder, that we would never take an L that's so high that we get collisions and things. Cool. Okay, I'll be inefficient. I'll write the thing here. Okay, quantum circuit. We'll have 3 registers, and they will have names and different numbers of qubits and things. So we'll have the weights register, which has log L qubits. We'll have the errors register that has M qubits. And we'll have the syndromes register that has N qubits. M larger than N, and everything larger than log L. There's a 5-step process, which you have in the thing. First step is, I call it amplitude encoding because I come from QML, but prepare a quantum state over L site, like L dimensions, whose amplitudes are the square roots of U, of the U case. This I call amplitude encoding. Then, no standard notation for this, I invented, do a controlled, like a multi-controlled Dickey state preparation, where if the weight register is in the 0 state, you prepare the Dickey state of weight 0, which is nothing. If the weight register is in the 0001 state, you prepare Dickey state of weight 1. And you do this for all weights, like for all k's from 0 to L. You do this in parallel at the same time. It won't be larger than M. It cannot be, no. L will be at most linear in M with smaller than 1 coefficient, and log L will be smaller than L. Okay, so at this point, we've taken care of this side of the story. And now, because this is how we roll, we have to uncompute the weights. I didn't have a better way of writing this, but like information flows in this direction. There's a bunch of C-notes, as you see, because all bit strings on the same branch have the same Hamming weight. And if you do a bunch of C-notes, you do the correct number of checks so that at the end, the thing on top becomes 0. And this you can throw away. Now, once you've done this, you take care of the phases. And this part is very easy. You just put a bunch of, like in the case of max Xor, this means put a Pauli Z for every qubit if the corresponding V is a 1, and do nothing if it's not a 1, and that does this part. Then, once you arrive here, you do the easy part of errors and syndromes, which is compute syndromes from errors. Information flows in this direction, and this is going from E0 to EBTE, which is the same as ES. All the things we did before that prepared the UK, the thing, and the thing, now we bring it to the syndrome register. And again, because this is how we roll, we need to uncompute. Uncompute errors from syndromes. Information flows in the opposite direction. And now we want to go from ES to 0S. And this is hard. This is a decoding problem. So like in this diagram, this is not the largest part of the circuit, but this would be the largest part of the circuit by a mile, where here we are calling a reversible version of the classical decoder coherently in parallel for all inputs at once. If this works, which we assumed it worked by assumption, so for all syndromes caused by errors of weight up to L, the decoder will be correct, and then this will result in a 0. And after all this work, we will have prepared the syndrome state. I call this the syndrome state. Now, we wipe the sweat from our foreheads, and we only have the easy part left, doing one layer of Hadamard, which is not the most quantum thing you've ever seen. Okay. The information flows in different directions. So this does something on this, and this does something on this. So at the end, there will be something here that wasn't here, so they can't cancel just from the input-output specifications.
Say you have E0 to ES, and don't put you have R0.
Yes. Yes. I mean, yeah, getting S from E, always easy. Getting E from S, hard.
I didn't see that.
Yeah. So congrats, we prepared the DQI state for Max Sorsat. And now we perform a computational basis measurement. We get a sample from this distribution, and that gives us performance, expected performance predicted by this crazy formula. And yeah, somehow in a nutshell, this is what DQI is. In the Max Linsat case, the Dickey step preparation gets a bit more complicated because you need to do a Dickey state preparation that's a uniform superposition over all non-zero symbols of a certain weight. The phases are not just depth, but they're a bit more fun stuff. And the decoder is inherently more complicated. Yeah. Yeah. You can do it on your laptop. It holds asymptotically, but yes. And there's a matrix of size L+1 times L+1. That's 3 diagonal. And the optimal coefficients are the top eigenvector of that matrix. It's related to the Jacobi thing of spin chains. Don't ask me what the thing is. L, M, N, no, L, M, and P. But it's not dependent on B nor V. Yes, but it's not that depending on your budget, you can increase L arbitrarily. There's an information roadblock of how many errors can be decoded for a given code. And that's specified by the problem. Different problems will give rise to different codes. So in principle, we assume that whatever L the problem gives us we'll be able to use that L. Like, because L will be we would like L to be linear in system size, and everything else is linear in system size. So the circuit complexity would be ideally linear in system size, or close to linear in system size.
So the worst case for given B is that equals 0, or am I wrong?
What does worst, like if there's a given B, there's no worst case. There are B's that correspond to very bad error correction codes, yes.
And L equals 0 corresponds to random value.
Yes. Yes.
There are B's that correspond with no correctable value.
I think the answer has to be yes, but that's not what I have been thinking. But yeah, I guess so. I mean, maybe not 0, but. And sorry, and getting high L is not enough, because so like there's the information bottleneck of how high L is for a given code, but you still need to find the decoder, the decoding algorithm. And so a good error correction code is one where the coding is cheap, so encoding is cheap, decoding is cheap, and correcting is cheap. It's very hard to cross all the three. And in particular, it could be that you get to an error correction code where analytically you know that that the maximum possible L would be very high, but there can be no polynomial time algorithm that can perform the decoding. Yeah. Here we, in all of this, we assume that we have a polynomial time algorithm that can decode up to L. So if you pick, like, it doesn't even need to be a property of the problem. If you get a good problem, but you use a bad decoder, then you have bad performance. Yeah. Exactly. Yeah, I think it's very related to imaginary time evolution in Hamiltonian DQI, which will be presented tomorrow in the learning seminar.
What's the rate of how much do we get back if we're happy with L equals 1 and if we're uncool take control from that the amplitudes are just as
I don't know what. Well, to prepare the DQI state for a given L, you need, then you need to decode all errors of weight 1.
Which might be more efficient.
I didn't think of it in terms of trade-off in this way, but yeah. And in practice, you would just try different L's and see what works best, I guess. Okay. We introduced Max Xorset, then we talked about Max Linsat. Now let's look for what the paper claims in terms of quantum advantage. And as I said several times, it's a game of parameter regimes. We don't expect a one-size-fits-all quantum advantage in general. Now, if you talk about max XOR set, we'll consider a specific case which is called random irregular sparse max XOR set, meaning B will be a uniform randomly sampled matrix whose sparsity distribution, as in how many ones and how many zeros you have in every row and in every column, will be fixed and irregular. So different rows and different columns will have different sparsity, but this will be fixed from the start. The dual to this sparse max XOR set problem is a low density parity check code. Parity check matrix, low density because the density of bits connected to checks is low because of the sparsity. And I will not write down all the things, I will just say it out loud, and if necessary, I can write down. One reason to use these things is because LDPC codes are well understood, and we have heuristic decoders that work very well on expectation. As I said before, the hardness of the coding is related to sparsity. So making the code sparse makes the decoding easier, but also it makes the optimization problem easier. In this case, the benchmark is beating simulated annealing, which I will not tell you about, but it's reasonable to understand that simulated annealing is a good representative for what a good classical algorithm would do. Now here, they want to find instances or distributions over instances where DQI does better than SA. And simulated annealing benefits from sparsity, but if you have a sparsity distribution where some rows and some columns are not sparse, then simulated annealing is not happy anymore. So the reason you do this, and the same thing is not true for the coding with LDPC, like the coding for LDPC codes. LDPC codes, if it's sparse, great. If it's less sparse, less great, but still good. So they use this irregular sparsity distribution to make the decoding problem easier without making the optimization problem easier for simulated annealing. And then the results they report for some system sizes are as follows. So DQI algorithm satisfies 0.831 fraction of satisfied constraints for like asymptotically in N and asymptotically in L. Simulated annealing does a bit worse. So they achieved their goal of finding finding an instance where DQI would be better than simulated annealing. But these are very fair people who wrote a very nice paper, and they made a very small change to simulated annealing, where classical algorithm, where they would take the sparsity distribution into account, and I call it SA+, they call it a tailored heuristic, which does much better than DQI, or a bit better than DQI. This is the formula, and these are numerical experiments. So all of this, sweat and tears for no quantum advantage. Yes. Sure, but we agreed that the figure of merit would be the expected value. Yes, agree. In DQI, there is no claim. In the DQI paper, there are no claims for quantum advantage in max XOR set. No. Yeah. As far as we know. Yeah, they for DQI, they run some numerics for estimating the largest L they find. And LDPC codes, we can decode the as an expectation, meaning for any one instance, if we demand correcting all errors up to a certain weight, that could be very small, but we add an epsilon and say how many errors we can correct with probability some epsilon, and then there's like a tolerant version of all of these formulas. So they do run, so they numerically check for the large instances what's the largest number of errors that they can decode with probability, with success probability 0, like 95%, which is reasonable, or 99%, I don't know. Okay, and we're almost at the end. Now we go back to Max Linsat, and I will show you something that does not look like Max Linsat at all. So this is the optimal polynomial intersection problem, which is a optimization problem defined on the cyclic group, but no high variable things, no high dimensions, just like you map FP to FP, and you specify some, like for every Y, you specify a set of outputs that you would like to see. And then the question is, can you find a polynomial that hits the highest number of this thing? And now I will write it a bit differently, and you will say, aha. So the coefficients of the polynomial are the variables that we're optimizing over. This is where you can more or less see where this could look like a Max Linsat problem. And then in the notation from before, now every constraint corresponds to a different input, a different element of the cyclic group. And the bit strings, like the x's, are the coefficients of the polynomial. This is a bit strange. And in particular, this corresponds to a Vandermonde matrix. And maybe you've heard about Vandermonde matrices in a different context, in that they correspond to Reed-Solomon codes, which I think are the ones in CDs or QR codes, or one of these. And Reed-Solomon codes are super well understood. They exploit algebraic structure instead of sparsity. And we know that the maximum number of errors decodable by a classical runtime decoder is n minus 1 divided by 2, where n minus 1 is the degree of the polynomial. So this matrix gives us the corresponding dual error correction code, which is a Reed-Solomon code. Yes, if you wrote this in the normal form, then the matrix would look like this, where gamma is a way of rewriting y. So gamma to the I would be each y. Okay. N is the distance, if I understand correctly. Yeah, I mean, this codes are great.
What is the number of bits?
Gamma to the I corresponds to I. And I is one possible value of y. Let's just it's a bit weird. Daniel, sorry. Okay, now the benchmark is do better than all known classical poly runtime algorithms. So not just a single good representative one anymore, but rather all of them. Yes. This problem had been studied before. Apparently not by many people, but there were results. And don't quote me on this, I've only heard this on corridors, but I think the story is the way I presented it is how it went, that they did all this blood, sweat, and tears, and then they realized that there was no quantum advantage for max exposure. Then they wrote the general version just because they can, and then they worried that nobody would care about this, and then someone made them aware of some corner of the classical literature where they said specifically this problem. So it was a lucky day that they could make claims for quantum advantage that would make people care, because people had committed to caring in that corner, sure, but okay. And for some parameter regime, DQI achieves 0.7179 fraction of satisfied constraints, and all known classical polynomial runtime algorithms achieve 0.55. And for a quantity that's bounded between 1/2 and 1, this gap is large enough that they claim exponential quantum advantage. And okay, and then in the paper they do a parameter like a resource estimation, because this paper was by Google, and Google have their flashy roadmap, and the question was, will this be a good candidate for practical quantum advantage within our roadmap? And the roadmap, I think, involves 1,000 logical qubits by 2030, and then they threw numbers around, and I think they have some instances that are supposed to use in the order of thousands of qubits. Also supposed to tell you the depth, but I don't know.
Do you know anything about
no. Of?
I mean, if I can solve the
Done? No, sure. These I don't know. These I don't know. I think this optimal polynomial intersection problem sometimes is called list recovery. So maybe if you want to help Santa Claus recover the list of good children, I don't know. But yeah, I have no idea. So that's why I'm saying that I heard this in the corridors about this corner of classical literature where they talked about this, but I don't know anything about this corner of the classical literature. Maybe Max. This is part of the tutorial. Last part is related work, which is a bonus track that didn't fit in the outline. So this paper is from summer 24, I think. Okay, I think I didn't spell it out. The paper is by Stephen Jordan and co-authors, published in Nature. And yeah, and since then there have been some follow-ups. I won't list all of them. You can ask ChatGPT for more of them. But the first one is, I think, related to the question Antonio was mentioning. Sure, the optimization problems are NP hard and stuff, but can we dequantize this? Can we spoof the quantum results by not like forgetting about solving the optimization problem, just get the information we have about this distribution and try to sample from it classically? And this is one of the papers that Max mentioned today in the group meeting. It's very nice, but the Bill Pfefferman group and some people from IBM. Then, and this is a question I've been thinking about also a bit, because kind of you could think if you could solve the optimization problem, then you would break the quantum advantage. If independently of solving the optimization problem, you could sample from the same distribution, you would also break the quantum advantage. But if you cannot solve it from this distribution, but you can sample from a different distribution, which is supported, or like, so here we have a distribution over X, but for every X, we have a number of satisfied constraints. So this distribution over X induces a distribution over solutions. We could perform like approximate sampling of this distribution in a way that we don't get close to this distribution in TV distance, but where we match the distribution over solutions. And this is the question I've been thinking about, like dequantizing, like trying to simulate the performance, trying to simulate the DQI distribution, but not using the TV distance as metric, but rather using the expected performance as metric, because that's arguably the weakest sufficient condition for dequantization. Not that I think it's dequantizable, but it would be fun to understand where the limits are and what are the bottlenecks. Now, the problem I presented of Max Lindstedt and Max Sorsat is vulnerable to
what is that?
They don't prove hardness. They fledge around hardness arguments, and they say we would expect this to be difficult, sampling from this to be difficult because this is very close to a uniform distribution over an exponentially large subset, which is unstructured, and which is an exponentially small fraction of the total. So just by kind of counting arguments. So like, if I tell you there's this probability distribution, which is uniform over an exponentially large subset, which is an exponentially small fraction, black box access, you cannot sample from it, even if you can compute probabilities. And they're arguing this is kind of that. But they say this is an argument, not a proof. I don't know. I would imagine no, but I don't know.
And this is why we say it's not like DPI will not.
No. This is what the DQI distribution is.
Yeah, but you cannot sample from it.
Classically, but you can sample from it with a quantum computer. Yes. So if we agree that optimization is like finding some spectral properties of a diagonal Hamiltonian, then you can go to non-diagonal Hamiltonians. And then you obtain Hamiltonian DQI, which is super interesting, and it will be presented tomorrow by Yihua, as we said. The reference is Schmid-Huber et al. 2510-07913. And then the last one, which fits the roadmap narrative. There was a new paper with several Google authors where they just specify for what problems where they claim quantum advantage, what they didn't. Okay. Yeah, okay. I'm done. There's this new paper where the main thing they do is make better resource estimates. Like Craig Eaton is one of the authors, so they get very deep. They don't talk so much about DQI stuff. They talk about how to most optimally call the one specific decoder for Reed-Solomon codes in parallel in a quantum computer. If you're into those things, super cool. But they make this point that if you list the candidates for practical quantum advantage in near term, and here practical means things like verifiable in the way Google calls it. So like factoring would be a practical quantum advantage. If you list the candidates we have with the new resource estimates and with the system sizes that seem to be enough to guarantee a speed up, an exponential speed up, then they say that DQI is the best candidate we have right now, which is big words by the people who will be running the circuits when it comes to that. For the relevant sizes. And so in this paper, they also prove that with their improved implementations, the quantum runtime of DQI is essentially linear in N and not quadratic in N, which is good. Yeah, I don't know so much about these things, but this paper seems like doubly cool, like at the practical level, but also at the roadmap level. And then there are other papers that I didn't list, which you can ask Max and Louis about.